Okay, cool. I guess I have to write something in the chat.
No, I'd already written that.
Okay, thanks. All right. So yeah, this session is about the third chapter, the linear regression. It's like the most basic tool or the baseline tool that you can go with when you build a model of your data according to authors. And so yeah, we have for this chapter there are seven research questions about marketing. It's about the relationship between the advertisement budget on some sectors, and between the relationship between advertisement and the overall sales in thousands of dollars. So the response variable would be the sales, basically. And yeah, we'll try to answer all of these using the linear regression tool. So it starts with the most basic form of linear regression, the univariate symbol or symbol linear regression. Of course, it's a supervised approach. You have the pairs of input and output in your data, and it's linear regression because it's basically a mathematical linear model, and the regression term comes from historical reasons in statistics, but it comes from a regression toward the mean, as mentioned by authors in the lectures. So basically, it's this model is just a linear relationship, mathematical linear relationship between the response and the predictor. And of course, you have only one predictor in the symbol case. So we read this mathematical equation as, like we say, for example, in our advertisement and sales example, we say that sales is approximately modeled by this equation, where X is, for example, the budget made or the budget for advertisement on newspaper, for example. And beta 1 and 0 are called the coefficients. Beta 0 is the intercept, and the beta 1 defines the slope of the line, because it just basically it's just a line on the plot, you know. So that's the assumption that we first made before moving to the before training our model. So the notation for our learned model is just basically similar to what we had in the linear model equation, except that we use the hat symbol everywhere on everything estimated. And so the goal here is to find the beta 0 hat and beta 1 hat based on the training data that we have. So, and also in addition to finding the or estimating the coefficients, we want to make we want to consider that the y hat will be as close as possible to the real y. And by the way, the real y is existing in our dataset. So there are many ways to do this, and the common approach is to minimize something called least squares criterion, which is in our case in the simple linear regression, it's called the residual. There is a metric called residual sum of squares, or abbreviated by RSS, which is something that we want to minimize. And in practice, this can be done automatically using libraries or statistical packages, you know. So RSS is perhaps the most important quantity in like when you speak speaking of linear regression, because it's involved in many other quantities, and as the name suggests, it's only a sum of residuals, and the residual is basically the difference between the real value of y from your sample or your data set, and between the difference between this and the predicted value that you have when you run your model. And after a lot of math, you will end up with these equations to calculate the coefficients that minimize the RSS. So any question or point to add before moving forward?
Yeah, just maybe a comment. I think with linear regression, we are interested with inference, right? Not much of prediction.
As far as I know, we care about two things, both of these. Like you want to predict y when you have your model, and at the same time, you want to interpret your model based on the coefficient. For example, in let me go up here. If x refers to the TV advertisements, then this beta 1 coefficient will can be used to interpret the the relationship or the association between the advertisement on TV and the final outcome, the sales, for example. So you focus on two aspects, basically.
So basically, we interested both with prediction and also doing some inference.
Yeah, exactly. Okay. So the next step after having your trained model is to assess the accuracy of coefficient estimates, and by the way, this is beneficial if you want to interpret your model. Okay, so the reason why we want to assess the accuracy of this is because the original model behind the process that generates data incorporate this epsilon term, which stands for the irreducible error, and this irreducible error has and also there are two assumptions made on this. I'll not go through this in detail because it's like a big topic, but in short, we assume that this error is normally distributed, and it has a mean of 0, and also it's independent of the predictor. And the problem is that the population mean of this response random variable would not be identical to the sample mean that we will have from our predicted y, which denoted by y hat. And to find this error, we calculate something called the standard error for each coefficient. And to do that, you start you first want to calculate something also called residual standard error using the RSS. And then for each coefficient, you can you would find the standard error using this equation also. And after having this standard error for each coefficient, you can form your like 95% confidence interval, which you can use to like make inference about the coefficient. For example, if the interval you have is very wide, then the uncertainty around the value of beta 1 or beta 0 is very high. Whereas if the confidence interval is narrow, then this is a strong a strong evidence that there is a significant association. So this is it in a nutshell. And also the standard error also has other usage in hypothesis testing, which is also useful for interpreting your model, and also for assessing the accuracy of estimates. And also in a nutshell, the for any estimated coefficient, you can do this these 5 steps to assess the accuracy of your coefficient. You first formulate your null hypothesis about the coefficient, and then you estimate the standard error based on this any of these equations. And after that, you compute something called t-statistic, which is later used to find another value called p-value, which is used to decide whether you want to reject a null hypothesis or not. And actually, this I think this is a very, very large topic, but according to the chapter, it's like when you have a p-value of some, if the p-value of some coefficient is less than alpha, which is some value that you propose, then we say that it has this predictor has a significant effect on y, like here in the table. For example, the coefficient for the predictor responsible for the TV advertisement, the p-value is less than 1%, which implies that there's indeed a significant effect on the outcome. So that's it in a nutshell.
Yeah, there. Just to add on there, we can also use even the t-statistics. Yes, because for the 95% confidence interval, if the t-statistics is greater than 2, then we could say that particular coefficient is significant, sort of. It has something significant here.
You mean that?
Yeah, even the t-statistics. Yeah, we could use it. I think there is a rule that says that, we could look at it from the t-distribution, the distribution, and I think there is a rule that it's around close to 2, the probability for the t-statistics. So if your coefficient is greater than 2, it's for the 95% confidence interval, then it's significant.
Yeah, that's right. You mean larger than 2 standard deviations?
Yeah, like larger than 2 standard deviations. Like
I mean,
the value of the t-statistics, if it's larger than 2 for the 95% confidence interval, yeah, we could, like here, the t values I'm referring to here.
Yes.
Honestly, if it's greater than 2, then it's for the 95% confidence interval, then it's statistically significant for that particular. Well, let's say for TV here, just looking at the t values, is t statistics is like 17.67, which is really high.
Yes.
Yeah. I'm not
honestly
sure.
I don't know how to deal with like the t distribution and t statistics directly, but I only know that b value is like the probability of the absolute value of t statistic, but I don't know about like t statistics in depth or in detail.
Yeah. Oh, yes.
Okay. I think this hypothesis testing is like a very large topic, and there is a dedicated chapter in the end of the book. Yeah, so let's see. So, and after assessing the accuracy of coefficient estimates, there is also another thing to assess, which is the accuracy of the model itself. And this step is also known as the model evaluation. And in this step, we want to find the quality of a linear regression fit to the data. So there are 4 quantities for doing that, listed in the chapter. So the first one is the residual standard error, and its interpretation is the absolute measure of the lack of the fit in your model. So small value would be interpreted as like that your model fits the data well, and it's measured in the same unit of y. So for example, if in our case y is sales, so if we have an RSE of 3.2, then this means this is the about units sold. And the second quantity is R² statistic, which is also calculated through these equations, and it's interpreted as the proportion of the variance in y explained by using the predictor in our model. And it's mentioned that it ranges between 0 and 1, but I read in other resources that it can have negative value in some extreme cases. But anyways, a good value of R² is relative to the application or the context. And the third metric is, the popular correlation, Pearson correlation coefficient. And in the case of simple linear regression, the R² statistic is identical to the like the correlation coefficient squared. And now moving to the to the multiple linear regression or multivariate linear regression, it's simply an extension to the simple case, but by adding more predictors to your model. And so you'd have the same notation, but with more coefficients and variable everywhere. And in the case, in case you are working on two predictors or variables, the model would represent a plane in the 3D space instead of a simple line. So, and you have also the same objective here. You want to find the set of coefficients that minimize the RSS, the sum of squared residuals. And here we also we make an important assumption, which is we assume that predictors are independent of each others, and there is no interactions between each other. And there are like some caveats mentioned by authors in lecture 3. Like they say that if there are correlations amongst predictors, this will lead to many problems in terms of inference and making inference and interpretations about your model, because and also it makes things complicated when you want to discuss causality out of your model, because there are a lot of things changing and moving in your variables. So here we make like an assumption that the predictors are uncorrelated. So basically the main rule here is that having more variables would lead to more responsibilities, because there are more things to assess basically. And in a nutshell, there are 4 questions to ask, or there are 4 questions to try to answer when you are working on multiple linear regression. The first one is about finding the relationship between the response and predictors, and this can be addressed like similar to what we did when we worked on hypothesis testing in the simple case here, but in the multivariate setting you would use the another statistic called F statistic, and then you would using the F distribution here, you will find the p-value that you will design based upon whether you would reject the null hypothesis or not. And the next question is about deciding which variables you want to include, which are the useful variables that you really want to include in the model to make it working better. So this is called the model selection problem, and there is a whole chapter on it. But in a nutshell, the first option is to like testing all possibilities of testing all possible models that you can build from all possible subsets of predictors. But this is, of course, inefficient in case you have many variables, because this grows exponentially. And of course, the second option and the smartest option, obviously, is to use like some variable selection algorithm. And the chapter, this chapter discuss three methods quickly, but as I said, there's like an in-depth discussion about that in a later chapter. So another aspect to another question to ask to your model, to your multivariate linear regression model is how well the model really fit the data. And R squared here is still working as in the symbol case, and it has the same interpretation. It gives you the proportion of the variance explained by the included predictors. But we add here like another variable, which here P stands for the number of variables included in your model. And the last question to answer based on the multiple linear regression model is about the accuracy of prediction made. And the predictions has like the prediction has multiple or multiple kinds of uncertainty. The first one is in the estimates of coefficients, and we use like the confidence interval here as we did in the symbol form of linear regression, to assess the uncertainty in the coefficients. And there's another source of uncertainty called the model bias, which is just caused by our assumptions about the process. And this is obviously cannot be as far as I know, is it cannot be measured or reduced. And the final is the irreducible error epsilon, and we use the prediction, something called prediction interval, to measure uncertainty related to that. And honestly, the chapter didn't explain this very well, especially this prediction interval. So I hope there will be like applications in the lab. So is there any question or thing to add before proceeding? Okay, cool. So now, after discussing all kinds of after discussing briefly all the all kinds of multiple regression, or at least the basic the basic forms, here are like the chapter starts to discuss some special cases. And the first one is like dealing with qualitative predictors, also known as the categorical predictors or factor variables. For example, you may have in your model, you may have like the gender, female or male, or the educational level. So these aren't quantitative, obviously. So there is like a way to handle that called dummy variables or one-hot encoding. So basically, if you have, for example, if for one for one qualitative predictor, if there are three possible values or levels, we introduce three dummy variables. So in this case, the like when one of these dummy variables is 0, it will be canceled out, and the other one will be 1. So it's like a computational trick to deal with the possible values of your qualitative predictor. And I think there are more tricks to do in when it comes to do this in action using Python or R. So this is a practical thing. And now the next section is about like removing some assumptions made at first. So here if we want to remove the assumption about the additive or the independence among predictors, we would introduce something called interaction effect. For example, in some cases, like one predictor is not fully independent from other. I think the book mentioned some example on the advertisement or something, but basically sometimes
you mentioned it gives the example of newspaper and radio advertising, stuff like that.
yeah, exactly, thanks.
Yeah.
Yes, so this interaction or synergy basically is modeled as like a multiplication between two variables. So this multiplication term like represents a new variable essentially, and it would have its own dedicated coefficient. And also there are many ways, many possibilities to do this. For example, you may have an interaction between a qualitative predictor and another quantitative, and so on. And
just to add, he also mentioned another example which I found quite interesting. It was they did a regression on ice cream sales and shark attacks.
yeah,
and they realized that was some kind of a positive relation.
this
So but then the problem was it was not because people consuming more ice cream was causing the shark attack. It was because it's ice cream sales increased during the summer, and you have more people at the beach, and then that's so you could see sometimes these interactions could be misleading.
yeah, exactly. Yeah, that's why correlation doesn't mean causation.
Causation.
Yeah, this is like an essential rule. And the second like the second settled assumption, let's say, is the linearity. So in some cases, of course, the relationship is not linear, and this can be like explored using the descriptive statistics and like just plotting the data, as you can see here. And
which is quite useful, like once you plot, because what you see with the visual, it gives you like a complete overview of the data, and then you could decide what to do. That's quite useful. And
exactly.
also I think he he's no, I forgot what I wanted to say, but like the visualization part you mentioned, it's very useful.
Yeah, exactly. And there's also this section. I found it very nice because it contains a lot of tips and tricks, you know, the about the potential problems. For example, here there is a tip in case you have nonlinear associations, you can apply some transformations, like instead of having the raw predictors, you can, for example, apply the logarithm or exponential, and you can have, for example, the association in a linear form. And I think there's a lot of discussions in this book about that in later chapters, as mentioned. So it also the other potential problem is the correlation of error terms, and honestly, I didn't get that fully because I found that section very brief, and it mentioned the something related to time series and autocorrelation or regressive, I think. Yeah, the next problem is for example, in this plot,
Sorry,
you
just to
yeah
add on to the note of correlation among the error terms. You know,
yeah sure.
if you remember at the beginning, you mentioned that the epsilon, it's
Mhm.
normally distributed with a mean of 0 and a
Yes.
variance. So, which is
Mhm.
implying that it's we made this normality assumption that the mean is 0 and the variance is constant.
Right, okay.
Yes.
Okay.
So if there is autocorrelation, this assumption is violated in a sense.
So
Yeah, so then we are
mhm.
into a problem. Our estimates could be biased in a sense.
Okay, I see.
Yeah.
Okay, I need to read that again. So
Yeah. So it's
th-
basically
thanks.
it violates an assumption we made at the beginning. So that's why.
Mhm.
Yeah.
Okay, interesting. Thanks a lot.
You're welcome.
Um, and yeah, here the other problem that you might face is when you plot the data, you would notice some pattern in that the variance of error terms or residuals is changing over fitted values, and like the way to reduce this is to apply the logarithmic transformation. So in this right plot, the resulted variance is much nicer, you know.
This
And
this is a this is a problem because it also violates the assumption of a constant variance.
ah
Yeah. So
so
this also violates an assumption we make of the linear model. So that's why if we observe something like that in the data, we have to look for ways to fix it.
so
So,
yes.
yeah, so because it violates one of
Mhm.
the assumptions that the variance has to be constant.
Cool.
Yeah, so the variance of the residuals has to be constant
I
over time.
you mean the constant assumption of constant variance in
Yes,
the
yes. So
epsilon,
because
right?
here it's somehow
Yeah.
violated.
Uh-huh.
So when we notice that in the data, we could try to apply some tricks like you mentioned, which applying the log transformation could be one of the tricks.
Okay, I see. I didn't realize that this is linked to the assumption about the
Yeah,
epsilon.
you know,
So
it's linked to the
yeah,
assumption. Yeah.
okay. Um, and yeah, next subsections is about outliers and like outliers over like predicted values and the predicted values and the predictors values. So so outliers as defined by the book is they are observations for which the true value of y is unusual given x, and this can lead, the presence of such values can lead to like bad value in like the evaluation metrics, such as residual standard error. So we need to identify these before fitting the model. And I think the way to do this is by plotting the, as mentioned, by plotting the something called studentized residuals, and looking for residuals that are larger than 3 standard deviations. For example, here in the plot, this this red point labeled by 20 is identified as outlier. So when plotting this studentized residuals, you will find it that it's really away from the bulk of data here. And here this concept, the high leverage points, is close to the outliers, but these points essentially are points with unusual values of x, of real x, without so it's like as I understand this, it's like the outliers in the values of x, without caring more about the y values. And this must be also identified before fitting the model, because like incorporating such values affects the slope of your line. And we compute something called the leverage statistic to identify these. And similarly, we plot the studentized residuals, as we did in outliers, to find the values that should be omitted from the data set.
Yeah, thanks. This is quite clear. You know, I didn't know of this technique before. Thanks.
Okay, sure, you're welcome. You know, actually, I'm really excited more excited about applying this in action, because I haven't did this before. All I know about outliers is like the traditional methods, you know.
Yeah.
If some value is away from the average, like 2 standard deviations, it's considered outlier. But here it seems these methods seem to be more advanced, you know.
Yeah.
Okay. So I guess the last issue, which is honestly it's the most complicated one and the most problematic one, is something called collinearity. And it's like essentially it occurs when the assumption of independence among predictors violated, and the core issue with that is when you want to interpret your model, it's hard to separate for example, the effect of x1 from the effect of x2. And it's, in a nutshell, it's addressed by doing one of these steps. You can either removing the problematic predictors or the highly correlated predictors. Of course, you need to first calculate the to find the correlation metrics, to find the correlation among all predictors together. The other option is to combine all these correlated predictors into one variable that represent them all. the other there's also another related issue called multicollinearity. Actually, I didn't get the difference between collinearity and multicollinearity. Maybe collinearity is only between two predictors and multicollinearity is between three or more.
Yeah, sure. That's it. Collinearity is just the simple correlation between two variables. Then multicollinearity is more than two variables.
Cool. So
yeah, so more than two, it's multicollinearity. Collinearity is just two.
Nice.
Yeah.
So because and I think because you have many predictors that have this problem, maybe it's hard to find the correlations among all of these. So there's like something to calculate, and it's called variance inflation factor, and based on this quantity, you can decide whether there is like collinearity between any subset of predictors, and essentially large value indicates the presence of that collinearity. So back to the first research questions in the at the beginning. We now have the like a big picture of the tools that we can use to answer each question. For example, a question about the existence of relationship between predictors and between, for example, the advertising budget and sales can be answered using like the multiple regression and looking at the F statistic, which eventually can be used for finding p-value and rejecting some null hypotheses that you define. And questions about the strength of relationship between advertising budget and sales can be addressed using the model evaluation metrics R squared and RSE, residual standard error. And speaking of the model selection and like questions about which variables to include in your model can be addressed by like basically by just looking at the b values for each predictor's t statistic. But there is an in-depth discussion in another chapter about that. And questions about the amount of association between predictors and the outcome can be also addressed using the confidence intervals on estimated coefficients. And like briefly, then if you have a narrow confidence interval, this would be a good or a strong evidence for having some association. And like if you want to actually if you want to assess your accuracy of prediction, you would use the prediction intervals. But actually I didn't find the chapter sufficient on very sufficient provided very sufficient points on this. Maybe this will be discussed in another place. And like simply if you want to find it, or if you want to check if the relationship is linear, you can just plot your data and like identify the patterns visually. And finally, the questions about synergy or interactions between predictors. This can be identified by modeling interaction, by basically introducing interaction terms, and also by testing the significance of interaction terms coefficient, of course, using something like p-value. The final section is showcasing a comparison between linear regression and the KNN, or key nearest neighbors. The goal is to compare a parametric method that is, of course, linear regression with another non-parametric method like KNN in our case. And the interesting benefit of non-parametric methods is that they don't make like many assumptions or assumptions about the form of real the real relationship between the response and predictors, like linearity in the case of linear regression. And it's essentially a moving average. It works. I think it works iteratively by finding the average over some key points. K is a hyperparameter that you tune, and it also determines the model smoothness, as shown here is in the plot. And it's like rule of thumb, you can say that the small value of k would result in low bias but high variance model, and vice versa if you have a high value of k. And the goal of this comparison is to like explain the bias variance trade-off in a more visual or a more visual way, I think. But it was mentioned in this section that parametric methods still outperform non-parametric methods if the assumptions about, for example, linearity and all of this stuff were close to the true function of, behind the data generating process. So I guess that's it for our chapter.
Yeah, that was a very good presentation. Thanks a lot.
Yeah, sure.
Learned a lot. Thanks a lot.
Sure.
Yeah. So I hope you will push this so that we could have this slides. I think they're very useful.
Yeah, of course. I'll do that.
Yeah.
Immediately. Actually, I would like to share something. I found this interactive like article. I think it's made by a project educational project by Amazon or something. So you can try, for example, training the linear regression step by step to build some like intuition about the process.
Cool. This is cool.
So
maybe you could share the link in the chat.
Yeah, sure, of course.
This is cool.
You may, of course, play with it, and if you are a visual learner like me, you definitely
of course I prefer stuff like this.
Yeah, sure. Actually, the whole website is cool. I think there are another article about variance bias variance trade-off.
Okay.
Yeah, this one. I'll share the links, and
please do that.
Can of course see that.
Yeah, I can end the meeting now.
Sorry?
Can I type end? Like, are we done?
Yeah, sure.
Yeah, okay.